What really happens inside the Java virtual machine? In this extended example, we'll build a miniature JVM, a full stack-based interpreter that executes compiled bytecodes. We'll design our own instruction set, write an assembler, and watch method calls and arithmetic unfold. Over 300 lines, we'll demystify the heart of Java itself. We start by defining every operation our VM understands. iconst pushes an integer constant, iload/store access local variables, arithmetic instructions manipulate the stack, and control flow opcodes handle branches and method calls. Instruction pairs an opcode with an optional integer operand. This is the raw material the interpreter will execute. A bytecode method holds a method's name, the number of local variables it uses, including parameters, and a list of instructions. VM program is the whole executable, a collection of methods and a string pool for method names, so that invocastatic can reference them by index. This separation mirrors how a real class file stores methods and the constant pool. A frame represents a single method call. It keeps an instruction pointer, IP, an array of local variables, parameters and temporary slots, and an operand stack. When the VM enters a method, it creates a new frame, and when it returns, the frame is popped. This is the core of stack-based execution. A frame represents a single method call. It keeps an instruction pointer, IP, an array of local variables, parameters and temporary slots, and an operand stack. When the VM enters a method, it creates a new frame, and when it returns, the frame is popped. This is the core of stack-based execution. The execute method starts by pushing the entry point method's frame. The main loop fetches the next instruction from the current frame's code, advances the instruction pointer, and dispatches via a large switch. If a method runs out of instructions without an explicit return, the frame is popped. This loop is the beating heart of the VM. These are the data manipulation instructions. They pop operands from the operand stack, perform the calculation, and push the result. isub and idiv carefully pop the right operand first to maintain expected order. dup duplicates the top of stack, a common JVM operation for expressions like x equals y, without reloading. Conditional jumps pop two ints and reset the instruction pointer if the comparison succeeds. ireturn ends the current method, it pops the return value, removes the frame, and pushes the value onto the caller's stack. This cleanly simulates how the real JVM handles method exits. Invocastatic looks up the callee by name, creates a fresh frame, and moves the arguments from the caller's operand stack into the new frame's local variables. Because arguments were pushed left to right, we pop them in reverse so that the first argument ends up at locals, 0. This mirrors how the JVM sets up a new stack frame. In build method, we walk the raw lines again. Labels are mapped to instruction indices. For jumps, we store a placeholder operand, -1, and save the label name in a parallel list. After all instructions are collected, we iterate again, replacing those placeholders with the real target indices from the label map. This produces a fully resolved bytecode method. Our assembly defines a recursive factorial method. It takes one argument, max locals equals 2 because we need one for the parameter and one extra for the subtraction result. The logic, if n equals 0, return 1, otherwise compute n factorial, n, 1. The main method pushes 5, calls factorial, prints the result, and halts. This small program fully exercises our interpreter. Compile with javac and run. The VM interprets the assembled bytecode step by step. Recursive calls push and pop frames, the operand stacks dance, and finally print outputs 120. You've just seen a complete, self-contained virtual machine in action, a perfect model of how the real JVM works.